This is the Water Technologies International Needs and Opportunities panel. This is panel 1 today. There are going to be 6 panels, or actually 4 panels and 2 roundtable discussions. So it's going to be a long day of talking about water technologies. And there's a lot to cover, lots of companies, lots of businesses. San Diego is a very interesting city for water treatment. There are about 3,000 people in San Diego who make their living in the desalination business. There are huge global companies like Nito Hydronautics and Toray. There are chemical companies. There are manufacturing companies like Applied Membrane. There are just a whole variety, and then subgroups and consultants and other organizations. And we tallied it up at one time, and there's about 3,000 people making their living. Most of them do their business outside of the San Diego area. They are international, they are global. And so we don't often pull a lot of them here because their customers aren't here. But fortunately today we've been able to bring some in, and we're anxious to hear what they have to say. Our first speaker is Mr. Gil Dhawan. Gil is a longtime fixture in San Diego in the desalination, reverse osmosis, water treatment business. He worked for Fluid Systems Division of UOP in the late 70s through the early 80s, working on some of the major wastewater treatment plants in the world in early days of desalination technology. There were 0 discharge plants built at places like the R.D. Nixon Power Station in Colorado and the San Juan Power Plant in Farmington, New Mexico. And these took boiler, feed water, cooling tower blowdown, and other wastewater from power plants and treated it down to 0 discharge using a combination of membrane processes and evaporation systems. And Gil was very much involved in some of the papers that were done in the early work in those projects. He also worked on some of the big seawater desalination projects that were emerging at that time, like the Jeddah RO and Umluj. He left Fluid Systems and started his own company, Applied Membrane Inc., and that's been about 4 decades now, I believe. And Applied Membrane is now one of the major companies in the world selling reverse osmosis membranes and systems, water treatment systems, and other solutions for a whole range of water applications. And if you see his plant in Vista, very impressive, a lot of work being done there and all. So I'm very pleased to introduce Gil, and we'll have hear what he has to tell us today. Gil?
Thank you. Thank you, Randy. I'm not the only fixture in this area. Randy himself is also. Randy and I have known each other for 40 years at Fluid Systems, and we have been working together ever since. So I was told that the topic was international needs and opportunities, and the time to spend on all of this is 12 minutes, so that's kind of a challenge in itself. So I will start with international needs. There is lack of water, scarcity of water, safety of water, water management, water treatment. These are the needs. Here are the facts, and all over the world, the water needs are such that they're getting more and more necessary to be taken care of in time that we have to not run out of water. So there are problems with drinking water, the sanitation, the treatment of the effluents, and basically all kinds of other issues with water treatment. So what do we do for water scarcity? There are all kinds of things to be done. And for example, water efficiency and how we use it, the utility operations, the monitoring and treatment. Some of this we heard in the panels before. Remote sensing of water, water quality control, water audit and efficiency improvement, rainwater harvesting, drinking water treatment, rivers and lakes protection, desalination, wastewater recycling, reuse. Now, water by itself is not the only thing that we need to worry about. Water and energy and food, they're all three related. And what we are looking at is how do we create more usable water? It's one thing to have all the conservation, all the other things we can do to save water, and also efficiency in production of crops, in food production. All those things are necessary to save water, but that's still not going to be enough water, because the projection is that by year 2030, more than 160% of the total available water volume will be needed. And this means that just conserving and efficient use of water is not going to do it. We must create more new usable water. And how do we create more new usable water? There are basically only two ways to do this: desalinate or reuse the wastewater. Then we have to look at what technologies can be used to reuse or desalinate. All of these technologies have been there, but there's always been improve efficiency. How can we simplify so places in the less developed countries can use these processes and basically reduce cost? Now, the technologies that are being developed in membrane area, the desalination area, are reverse osmosis pretreatment, options to make reverse osmosis more cost efficient, new membrane materials that can do more than the current membrane materials can do, sometimes combining some of the electric current, pressure, and other possible ways to improve membrane performance, high recovery systems to use more of the water as permeate and less as concentrate. And these technologies are being developed by various companies, including such as minimum liquid discharge, zero liquid discharge, flow reversal, max H2O, CCRO. There are a number of these. Solar evaporation, electrodialysis, and ion-specific membranes. Now, one of the things that people always talk about in desalination is the use of energy as being a problem, high energy usage. So there are two ways to look at it: improve the membrane technology to make it more efficient, or maybe make the energy less expensive. So a lot of work is being done on energy sides, like hydrogen generation and solar power and wind power and using the wave energy of the ocean. So let's not just put all our effort to make the membranes or the treatment more cost effective. If energy usage is causing the problem, why not make energy less expensive? Because that would accomplish the same thing. So this is happening in many ways. And so one of the things we have in the membrane side to improve things is ion selective membranes. This is being done to make sure we can make it more effective to remove what we want to remove, not everything. New membrane materials, that will help also the membrane separation or desalination more cost effective. Number of companies are working on this. And this is all very exciting because for many years, very little work was being done on new types of membrane materials, even though it's quite known that the current materials have limitations. So in the last few years, suddenly there is a lot more interest and a lot more effective work being done to make more effective membranes that might help. And these are companies like Zwitter, Aquaporins, and others using synthetic nanochannels, graphene, and also coating membranes, membrane surface modifications. So what I'm describing here are kind of opportunities to make the desalination part of the creating new water more effective and possible in places where energy is very expensive. Solar power. We got a request about 10 years ago to provide 350 solar powered systems for Iraq. And the issue was 350 villages had lost power, electric power, due to the war. And so now they didn't have any water to drink from the water system supply. So they were going to the river and drinking that water, which was polluted, and they were getting cholera and other diseases. So we were approached as a company to supply 350 solar powered systems, about 50,000 gallons per day each. And they told us they needed them in a hurry because the people were dying. And I said, how fast do you need them? And I said, 4 months. 4 months, 350 solar powered system with the specifications like you're looking at, all tailor mounted, enclosed with a sheet material so that people won't steal parts of this. And we said 4 months is not a long time to be able to provide you 350 solar powered systems all built like that. So I didn't want to say, yes, we can do it and not be able to do it. So we turned it down. But they said, no, you got to help. It's a question of people's life. And so I didn't know how politely to tell them we cannot do it. So then I said, okay, we'll do it if we can have, the total project was $12 million. I said, we can do it if you have $6 million in our account in 2 days. So I said, okay, this is a nice way to say no. But to my surprise and shock, there was $6 million in 2 days. And I didn't know how they did that. You can't even transfer $6 million in 2 days within the town itself from here, from one bank to another. Then I found they had a friend in La Jolla who owned the Boston Market restaurant chain. He just transferred his $6 million and figured out how to get it back from the Ministry of Electricity and Water in Iraq. And so we got 2 empty buildings that were for lease close to us that I said we needed to lease it for 4 months. And they allowed us to hire 25 people, work 7 days a week, 24 hours a day, and made it happen. 2 minutes left. So this is another way to get energy, low cost. Water waves. The way this works is water waves pressurize through a pump. It looks like a piston pump. Every time the wave goes up, it pushes the piston up and so on, and creates energy at a lower cost or very low, almost no. The second part that is to create new water is water reuse. And this has many possibilities. Direct purification like Orange County Water District, and other reuses like we have here 6 million gallons per day system with zero wastewater. This is for agricultural use, and it included nanofiltration, reverse osmosis, ion exchange, and seawater reverse osmosis. The total integrated system kept the farmer growing a crop that was going to be otherwise shut down in business by using this technology. Then we have another one that was used in Cedars-Sinai Medical Center. And
California is still in a drought. A local institution is showing off what's described as a groundbreaking water conservation facility. This is what the plant in the Fairfax district looks like. Administrators tell us because Cedars-Sinai is in a low-lying area, they have to constantly flush out groundwater into the storm drains. Well, the new plant will now reclaim that water for use throughout its cooling towers. That's expected to slash its water use by 29 million gallons each year. That's enough to supply nearly 300 homes for a year.
And this is indirect use, where water is basically after normal pre-treatment is put down through the ground, and it's the kind of thing being used at Orange County Water District. New technology in the wastewater being developed. And this is an interesting one, whereas this biofuel is being created as wastewater byproduct, because many people are looking at wastewater as not just wastewater, but as a resource to get either minerals out of it or other ways to use the wastewater and create, and don't think of it as a waste, but as a resource. So this one has a system with a canal dig inland, and the water is then collected in ponds, and then that wastewater from the raising of the shrimps and fish is taken and diverted to fields and planted in this special material, Salicornia, a saltwater tolerant plant that grows in such climates. And this is then harvested for its oil, which is then refined as a biofuel. So you took wastewater, converted it into one that could be used for aquaculture, and then took that and created another plant and used that to create oil, became a biofuel, and it's the best use of wastewater. So these are some of the things, I won't go through it, that all the countries are doing to create reuse water and to save water. And I will end this with this Singapore slide that I'm sure Randy is going to also talk about later. The whole idea is to make everything water-wise, make the buildings water-wise, and make the industry and the water use in the industry water-wise, so it can be recycled, reused, and the wastewater is not thought of as wastewater. And that's all I have. Thank you.
Thank you, Gil. And as you can see, it's difficult to cover the breadth of topics Gil has in 12 minutes. So, and it is, it's part of the challenge. One of the things Gil mentioned was a couple of companies, Switter and Oneka, on the system, and those representatives from those companies will be here this afternoon making presentations. So you'll learn more about Switter and Oneka as we go forward. So thank you very much, Gil. I think we'll hold the questions and answers till at the end, and keep moving forward. And thanks again. Our next speaker today is Professor Eric Hoek, Ph.D. from UCLA Samuel School of Engineering. Eric's a bit of a legend in the water business, as is UCLA. UCLA for years has done tremendous work in desalination and membrane technology. The first company I worked for, General Atomic, in 1969 was using the Loeb-Surarajan membrane, which came from UCLA, and we paid royalties to UCLA. Then McCutcheon did work, and we paid royalties to McCutcheon, and we worked with other people at UCLA. And Eric has carried on that tradition and even done more with it. Eric developed a nanotechnology approach to changing the polyamide membrane, which is the dominant membrane in reverse osmosis desalination. And that nanotechnology, it was something that was not thought about by anybody that I was working with or knew about. We were sort of surprised when it came along, because I wasn't sure how you could modify the thin film composite polyamide membrane, but Eric figured out a way to do it. And it reduced energy consumption by about 25%. And I think when it first came out, and I had left Toray at that time and went to work for the company that was promoting this called Nano H2O, and using Eric's technology, with a license from UCLA. And we sold these products around the world, and our competitors would say, we don't see anything different that you're doing. We can't find anything in this membrane, and we sort of ignored them. But all I can say is that there was some different stuff that we followed Eric's teachings, and the membrane did improve or have lower pressure requirement by about 15 to 25%. And I'll give you two quick anecdotal stories before I let Eric take over. We sold membranes to Courcelles, and I'll call the company that we sold them to Company O, and they were selling it to Aqua Electra, which is the primary water provider in the island of Courcelles. And they had 4 RO systems with different people's membranes in them. We loaded up one train. And Company O said, you know, the pressure you said is good, that's fine, but your permeate's 150 ppm and our spec is 120, so you're not meeting spec. So we felt bad about that and went back to El Segundo and made a whole new load of membrane to send to the site to replace that membrane on a warranty basis. We got to the site and started to load the membrane, and Aqua Electric came in and said, no, don't touch those membranes. And Company O said, well, why not? This is our customer. We said, because it's 25 to 30% less energy than we're using on any of the others, and we don't want those elements removed. They're making good water at much lower energy costs. And in fact, take those new membranes and put them in one of the other plants. And so we did. This same thing was repeated in other places, including Palmahim, which is one of the big seawater desalting plants in the world in Israel, and where we completely changed out a train of membrane, 2,800 elements for a tune of about $1.9 million. And it did the same thing. And so Eric made a great impact on the business, and it's part of what Gil was mentioning, and that is new membranes, new membrane approaches are reducing energy consumption and making the technology more usable. Eric continues to focus on research for membrane formation, applications of energy, water, human health, and environmental protection. That's his focus. And he's recently published a book called Sustainable Desalination and Water Reuse. So Eric, please come up and tell us what you're doing.
Thanks, Randy. The organizers, Matt, for pulling this together and having us all here today. I'm going to have a slightly more focused talk, and not so much, not specifically about my own work, but sort of a perspective on some of the advances and challenges in brine management. So before I do that, I want to plant kind of the seed of an idea. So this is a quote from Adam Smith in the late 1700s. Nothing's more useful than water, but it will purchase scarce anything. Scarce anything can be had in exchange for it. A diamond, on the contrary, has scarce any use value, but a very great quantity of other goods may be frequently had in exchange for it. So this was deemed the diamond water paradox. I'm going to introduce to you the everything water paradox. So I did some Google searching and found out the prices of things, different materials that are in water, right, including water itself. And then also, this comes from my LADWP bi-monthly bill. I pay about $3 for a ton of water, right, which is an incredibly good deal, considering to dispose of salty water, you pay about 3 times more. A clean sodium chloride brine is almost 10 times more valuable than fresh water, which makes no sense. Ag lime, gypsum, a clean calcium chloride brine, almost 100x clean water. Ammonium sulfate, which you can extract from wastewater. Forget about bottled water. Hydrogen, 1,000 times more valuable than clean water. But what is water made of? 2 hydrogens and an oxygen. Volatile fatty acids like acetic acid, propionic acid, these can be sometimes used directly for animal feed. Also, they can be upgraded to things like jet fuel. Again, about 1000x, a little more than that. Metallic magnesium, and finally, lithium carbonate, the stuff that goes into the batteries in your cell phones and Teslas and whatnot. So lots of possibilities here with respect to all the stuff that exists in different water sources, whether it be it brackish groundwater, freshwater, seawater, wastewater, what have you. Okay, so keep this in mind as we talk about how do we manage the brine. So Gil really painted the picture, so I'm not going to spend too much time on this, but we're constantly tapping into alternative water sources, brackish groundwater, municipal wastewater. The city of LA, the county of LA have committed by 2035 to recycle 100% of our wastewater. Right? So this is happening in massive amounts. And the predominant technology for all of these, converting all these water sources into something useful is reverse osmosis membranes. When you look at, for example, the operating costs for brackish water or industrial wastewater, something like that, treating it with RO, you can see the blue sort of half circle. That's the cost of getting rid of the brine, right? Everything else is the energy, the labor, the consumables, chemicals, right, what have you. But the brine management is really, it's the dog. It's not the tail that wags the dog. It's the dog, right? So how do we manage the brine? Traditionally, we have deep well injection. If you're coastal, we have brine lines. If you're at a desal plant, we can send it out into the ocean and disperse it. We have evaporation ponds, and we have these thermal technologies that either concentrated up further or precipitated out into solids, an evaporator and a crystallizer I'm showing there. So this is kind of what we do today. There've been a number of process technologies that have been out for 20 plus years. Hero was initially commercialized by GE, high efficiency RO. Basically, a lot of ion exchange softening to take out the minerals, which tend to form a scale on the membranes and prevent you from getting very high recovery. So for those of you who aren't experts in reverse osmosis or desalination, recovery means you feed a certain amount of water into the membrane. Some of it goes through the membrane and some of it doesn't. And so you end up with two streams instead of one which is a clean product and one which is a concentrated version of what you fed in. Okay? So to get high recovery, we have to take out the minerals. There's another way of doing it. This was optimized pretreatment and unique separation. Is the English interpretation of the French from Veolia, but this was Opus, they called it. And again, chemical softening followed by filtration and then high recovery RO. There are things like Max H2O, which Gil mentioned. UCLA in the early 2000s, Yoram Cohen was developing this interstage demineralization where you run primary RO at fairly low recovery, 50, 60%. Then you demin and have a secondary RO process. So lots of ways to get to higher recovery, right, through process innovations. One of the keys that seems to be emerging now is in order to get to lower energy consumption, lower capital cost, is membrane brine concentration to displace that traditional thermal evaporator. And companies like Hydronautics and now DuPont, they have high pressure RO membranes. Other companies are coming out with such membranes. They can operate up to 1800 PSI. For some perspective, that's almost 2x what a seawater desal plant operates at. So traditional process technology, this is showing the feed water coming in, the RO membrane, product water is in blue, and the concentrated water or the brine is in red. And the traditional approach to getting to higher recovery is you add on more stages. So the concentrate from the first stage goes to a second stage, is further treated, combine the permeate streams, that's your product water, and then you've minimized the amount of brine. That can only get you so far, typically somewhere between maybe 60 and 80% for most of these kind of waters that we're dealing with. So there are these new emerging process technologies like closed circuit RO, again, Gil mentioned. osmotic assisted RO, cascading osmosis mediated RO, counterflow RO. They're all different versions of the same thing. Low rejection RO, high pressure RO, ultra high pressure RO, high pressure, low rejection RO. You get the picture. Okay. So anyway, so the point is that people are really now that this problem of brine management is so important, it's so expensive, right? That these kind of, honestly, 20 years ago, ridiculous and crazy process concepts are actually feasible, economically feasible, right? And so companies are out there developing these process technologies now. And they all can, the goal is to, with a membrane, concentrate up a brine to about 250,000 milligrams per liter. So then it can be fed into a thermal crystallizer and you end up with dry salt and some more fresh water. Okay, so why aren't we already doing it? First of all, when you're dealing with a concentrated brine, 100,000, 200,000, that's 10 or 20% salt. That's only 80 or 90% water. I mean, that's a barely water at that point. It's really viscous and it slows everything down such that, again, for those of you who know, like Gil and Randy, concentration polarization is a thing that academics talk about a lot. This is the first application I've ever found where it matters. It actually does matter. And it actually limits the water recovery that one can achieve in concentrating brine. In addition, these are scanning electron microscope images of a pristine, what's marketed as a high pressure RO membrane, before and after pressurizing to 3000 PSI. And so you can see the physical cross section is reduced. And if you look at the top layer here, it's pretty highly densified, right? And that really kills the permeability of the membrane. So for whatever pressure you're able to apply, you're just getting a trickle of water through the membrane, right? Instead of a flood. And you really want to keep the flux high. In addition, on the backside of the membrane in these spiral-wound modules are these we call trico mesh or permeate carrier materials. They're meant to exist between the membrane sheets and allow the clean water to just kind of spiral through and empty into the permeate core tube. And you can see different sort of weave patterns here. Well, under high pressure, this is the top side and the back side of a membrane. The membrane becomes physically embossed in the pattern of the trico mesh. And when that happens, the tensile forces causing the membrane to have this curvature can rupture the membrane. And you can see here, this is like 100 micron size defect that forms, and the rejection starts to just go way down. And so there's compaction and embossing are really the enemy of high pressure reverse osmosis membrane operation. Okay, now this is some work that's been done by other folks looking at the price per kilogram and the concentration of stuff that's in seawater, right? And this red dotted line is kind of the line that demarcates economic feasibility, that whatever the constituent is, lithium, magnesium, it's sufficiently valuable and there's sufficiently enough of it that you can economically recover it, right? If you're on the left side of this line, it's a little more challenging and probably not going to be worth it, at least at this stage. So, but a number of things that folks are targeting for recovering from seawater, for example. And this is an example from Saudi Arabia, where they have massive amounts of desalination being done. They also have chemical industries like chloralkali production and bromine production for industrial applications. Large markets, and the key is the selling price, say $65 to $75 a dry ton for high purity sodium chloride, and the production costs are in line such that you can make a profit selling the salt, right? Same thing for bromine. The production costs are much lower than the market price, right, for this commodity. So there's economic feasibility here. And this is another example where they're essentially showing that from, this is the global sodium chloride market, 330 million dry tons per year. 100,000 meter cube per day seawater plant can produce about 1 million dry tons per year of salt. So a fraction of the total global market demand, right? But at a production cost of about 60 cents per cubic meter processed, that's $22 million a year. And the brine sales revenue, $65 a dry ton, gives you 65 million a year. Even if it's $40 a ton, right? You can cover the cost of water treatment. You can actually make more money selling the salt than it takes to pay for the desalinated water. There's a European Union initiative similar. It's called Sea for Value, targeting these particular elements in seawater to be harvested and productized. So I'll end with this. It's kind of just meant to be thought-provoking, but are we asking the right questions? For example, should we be paying to treat water and paying more to manage and dispose of the residuals? Or should we be getting paid to harvest these high-value materials with clean water as a residual that we can give away for free? So, thank you.
It makes me think we've been looking at the wrong end of this thing. We've been looking at the price of selling water, and you're suggesting we should look at the other. That's very intriguing and certainly true. Reverse osmosis and desalination technology have been used for mineral concentration for a long time. There are lithium production plants in Bariloche, Argentina, using reverse osmosis membranes. And we talked about geothermal. I heard people discuss geothermal today and removing lithium from them. You can also get zinc and nickel, I think, from geothermal wells. And in fact, there was a plant in Calipatria that was doing that. And of course, copper has been mined that way for a long time. So certainly it's been done, but the scale you're talking about and some of the other minerals, that's tremendous and very interesting. Thank you, Eric. Our next speaker is Patrick Courcelles. He's the Counsel and Trade Commissioner for the Consulate General of Canada in Los Angeles, Global Affairs for Canada. Patrick's been the counsel since 2019 and covers the CleanTech sector, which is what we're part of. He previously covered CleanTech in Canada, Sao Paulo, Brazil, and Guadalajara, Mexico. So he's been around. Do you speak all those languages, Patrick? Oh my gosh. All right. Well, so he is very knowledgeable. He helps Canadian companies do business in Southern California, Arizona, and Nevada. Patrick?
Thank you very much. It's a pleasure to be here today, and thanks so much for TMA BlueTech for the invitation, and pleasure to be on a panel with some esteemed people who know a lot more about water than I do. But yeah, it's a pleasure to be here today. I wanted to take a few minutes today just to talk a little bit about Canada's water and wastewater sector, talk a little bit as well about Canada's water technology and some of the applications, some of them that have been done already here in Southern California, and also to see or really discuss how Canada, the US, and other countries around the world should really be working together to solve some of these issues that my other colleagues have been talking about. So let's get started. As some of you might already know, Canada really is a water superpower, not only because we have 20% of the world's fresh water, but arguably, I would say, also because we are one of the 8th biggest water market in the world. We have over 700 companies, water technology companies, in a range of sectors and markets. Spend a lot of money on research chairs in the water space as well. And because we are such a small market, smaller than the California market, many of our water technology companies actually export. And I'll talk a little bit later about some of the examples of some of those water tech companies that have been very active here in the Southwest US. Just to give you a little bit of an overview of the water and wastewater sector in Canada, we have 2,500 municipally owned water and sewer utilities. Very rare in Canada for the private sector to be running the utilities across the country. Just has not really happened, although there is obviously a big role for the private sector. So water technology companies, companies that might build some of the utilities operations, but normally they're operated by our municipalities. 32 million people are getting their drinking water from plants. 30 million. I tried to convert these into imperial because normally we have everything in metric in Canada, but I hope my conversions were right. 30 million served by municipal wastewater systems, and our average residential water use is 57 gallons per day per person. The Federation of Canadian Municipalities in Canada did identify a few challenges that we do have and some priorities in Canada. These are areas where, for example, if you are an engineering company, if you are a water technology company, and you might have solutions in these areas, then potentially Canada would be an interesting market for you to explore and possibly invest in. So some of the challenges are asset management, financial sustainability, and need for resilience. And as you can see here, different priorities in managing urban flooding, increasing system resilience, reducing operating costs, energy being a huge factor there, and undertaking proactive management. On the water technology side, as I was mentioning earlier, Canada is quite well known worldwide on developing some water technologies. 700 plus water technology companies, many of them startups, but also some mature companies. I will give some examples a little bit later on of, as I mentioned earlier, of some of those companies that are already working in this region. And I was very happy to see in Gil's presentation earlier, one of those companies being highlighted, Oneka Technologies out of Montreal, for water desalination using wave power. We also have many enablers within the ecosystem, different accelerators, industry associations. And one of them that I did want to highlight, we have an accelerator, a CleanTech accelerator in Canada called Foresight, and they have Water Next, which is like a water hub, if you will. And they actually provide a lot of the information for this presentation. So you might have come across them. And then also academic institution, government, and not-for-profits that are part of that ecosystem, that very rich ecosystem as well. Some of the strengths of the water technology in Canada, membranes was one of them, filtration, we've been talking about membranes a lot, but there has been a lot of Canadian leadership in the membrane space. We can look at energy efficiency technologies. I know those are some issues here in Southern California with the use of energy, and especially with a lot of electric vehicles coming on board, many discussions about the stress on the energy system. So energy efficiency in water is obviously a very big area. Water reuse is something that we've talked about as well today. Pipe inspection and leak detection, as is the case in Canada. I know in many US cities, a lot of the infrastructure is quite old. We don't always know where the leakage is happening. So there's some very innovative technologies coming out in that space as well, digital solutions as well. There's some examples in all of these categories that we can look at, but those are just some examples of the areas of strength of Canada's technology. Now, I wanted to also highlight some ways to work with Canada. So whether you're a utility or an engineering firm that might be looking for solutions for a tough problem. I've been working with a company based in Southern California, an engineering company recently. They've been working with a utility that has some very specific problems that they haven't been able to solve yet. They approached us and we're introducing them to a couple different Canadian solutions that might be able to help. So that's a way that we can definitely help, one way that we can help. Also companies that are maybe looking to collaborate on furthering research and development. That's another area where we'd be happy to assist you to identify a Canadian partner, whether it's on the academic side or on the private sector side, to do some further R&D. Or if you're a technology company or an engineering company and you're looking at opportunities in Canada, we can help you identify partners or identify locations to potentially invest in Canada where some of those solutions might be needed. Feel free to reach out to us. I have business cards. I'll have my contacts on the next slide, but we'd be happy to assist there. And I think one of the main messages we want to pass on is, I think there's a lot of value in collaboration, and I think that we saw that, even in the most recently in the pandemic, international collaboration on vaccines, on different solutions. While we know, and as Gil was mentioning earlier, the crisis that we're looking at in the water sector, and I think through international collaboration, we'll be able to find the solutions. I also wanted to highlight a couple of upcoming events that the consulate is actively involved in. Some of you might participate in WEFTech each year in the fall. We normally have upwards of 100, sometimes up to 150 Canadian water technology companies that participate in that event. If you plan to attend, we'd be happy to make introductions to any of those companies if you're interested. And we also, the Canadian Consulate here in Los Angeles has been working on a Canadian Water Innovation Roadshow. We've done this in Southern California a couple of times already. Once was virtual during the pandemic. We've done it in Arizona and Nevada as well, where we work with local utilities to identify some of their main challenges, and then we recruit companies based on those challenges to come down and meet with utilities. So we're actually working with a few utilities in San Diego region, Ventura County, Santa Barbara County, and of course, LA on this roadshow that'll be taking place in March. So happy to have you guys involved as well, anyone who might be interested. The utilities also help us choose which companies are chosen for the roadshow. So we're actually in that process now of starting to recruit and then select those companies that'll take part. And I just wanted to highlight a couple examples. Oneka was one that fortunately my colleague Gil did present, but a couple of the companies that have had some success here in Southern California, just a couple examples. Fred Sense, a company out of Alberta that does monitoring of different elements in water with field kits. So these are a tiny little box about this size that utilities or engineering firms can use to test water in the field, can get results in minutes as opposed to days, which is really exciting. They've participated in past editions of our roadshow and have been selling these kits to many utilities throughout Southwest USA. But we're also chosen by the Port of San Diego with the help of my colleague Mario at the back here, who Mario is one of my colleagues who works in our consulate here in San Diego, who linked them up to the Port of San Diego, and they've been doing an ongoing pilot project with the port over the last couple of years. Deep Trekker is another company, that one out of Ontario, that does different pipe crawlers, robots, underwater robots and cameras. Robots are always really cool to see. And they've sold, again, they participated in our previous roadshows, and they've sold a few of their units to, it's not public information, but to some very large utilities, we'll say, in Southern California. So again, I mean, I think, as I mentioned earlier, and the real point that I wanted to make today is that collaborating, I think we can, better solve or more easily solve some of these major challenges that we have in the water space. I encourage you to reach out to me if you have any interest in collaborating with Canada or Canadian companies or investing in Canada, and happy to answer any questions you might have as well. Thank you so much.
Questions, if we could, for either Eric, Gil, or Patrick. Do you want us to use one of the microphones?
Please,
okay.
Yeah, for the online audience.
Are they on?
Yes, sir.
So, would anyone like to ask a question? I have the microphone. I'd be happy to hand it to you.
I have a question.
Sure. Yeah, this is for Eric. In your presentation, you're talking about some of the optimization schemes for the current RO systems, and specifically around, it looked like deionization for preventing scale in the membranes. And I was wondering if you could speak to what that does to influence the mining products that you could then recover from wastewater.
So the traditional processes that I showed were not developed for harvesting anything of value except water. And so whether you're using chemical softening, ion exchange resins, nanofiltration, whatever it is for the pretreatment to remove the minerals, then that becomes a waste stream traditionally. And then you go on and water is considered the product of interest. There are folks around the world now that are changing that. For example, the Saline Water Conversion Corporation in Saudi Arabia, they treat seawater mainly, and they do nanofiltration in front of the RO membranes. The nanofiltration removes the scaling minerals in the form of divalent cations like calcium and magnesium, and anions like sulfate. And so that gets separated, and then you have mainly sodium, chloride, a little bit of potassium, and then trace elements that go to the desalination step, which is seawater RO membranes. The product water comes out, and then the concentrate from the nanofiltration gets further concentrated at really high pressure. And they have a customer who buys that divalent stream. And then the brine from the desal stage gets further concentrated, and it's 95% sodium chloride, and they sell that to a chemical company called Sabec as the feedstock for chloralkali production, where they electrochemically make bleach and caustic, which is alkaline chemical, high pH. And so the profits from selling the brine and the divalent stream more than pay for the whole water treatment operation. So I think we're going to see more of this over the course of time, but it's historically been really just all about the water, right? And everything in water is treated as something that's you just want out, right? But now we're starting to see there's so much value in some of the things that are in water that the whole process designs are being reconceived to enable that recovery.
And the technology's improved to go to higher pressures so that you can concentrate those things even further than we used to be able to.
Yeah, absolutely.
That 1800 PSI you were talking about. Another question? Yes, sir.
This question is for the panel. So I think it's clear that we need to look at all sources for RO. But wondering how much focus is on desalination and how much the industry is focusing on potable reuse and treating fresh water, because it seems to me it would take a lot less energy and resources to clean already fresh water versus ocean water, salt water.
I'll take an early stab at that and then hand the microphone off. The biggest market for desalination technology right now is seawater desalting, and it's growing very rapidly. Historically, when the business started, it was all brackish water desalting. We were treating groundwater from Florida and other places in the world to make fresh water from groundwater, brackish water. But as seawater came along, the volume is so much bigger, the need was so much greater that it transitioned to that whole seawater market. And wastewater reuse was started in 1977, but has really caught fire in the last 20 years, where you take sewage and reclaim it. And that's, again, a brackish water kind of membrane, a lower pressure membrane. Treating fresh water, like city water, with membrane processes has been done for a long time, but it's usually used for industrial applications like ultra pure water for the semiconductor industry, or for boiler feed water, or processed water, or even breweries or water companies who make bottled water. If you look and read the labels on those bottled waters, you'll find almost all of them have been processed by a reverse osmosis plant. So that's pretty typical for what's going on. But right now, seawater desalting is where the growth is. It's about 20% a year. You want to add to that, Gil?
Yeah, I think some of this is on the availability of what you have. Like in Singapore, the only source of water they can make more water out of is wastewater. They don't have the other sources. And some places, this river is what the thing closest to you. So you use this to create more water. Some places you don't have either river or the ocean. So well water is all you have, or water reuse is all you can do. So it also depends on the sources that you have available to you to get the new water, not just the cost of which water is easier to treat compared to other water, but what do you have to work with?
Anybody else?
Can I make a point?
Sure.
So I think just kind of agreeing with what Randy said and Gil. But if you look at the whole global scenario, you have 71% of water, right? When you talk of Earth, but only 0.7% of this is kind of available as fresh water. So if we speak of surface water, groundwater, but when you look at desalination, I think the point which was kind of made here was you also now need to focus on the brine, because that's the major composition, right? And I think there are now technologies to kind of treat groundwater and surface water. but the dynamics remains the same, where you need to kind of take care of the microorganisms, the bacterial contamination, the organics. So I think these are all different possibilities which are definitely there.
Thank you, Dinesh. Well, I think in the interest of keeping to our schedule, we'll have to end our session at this point. This is the end of panel 1. Thank you very much.